Okay, so this is my second take on this. I was recording and I was halfway through and I realized that it stopped because the file was full. I didn't realize it. So I'm back. Okay, we're covering lesson 6.1 today. Get rid of that. And it is about differential equations and slope fields. So any equation that involves a derivative is called a differential equation. And if you know anyone majoring in math or statistics or engineering, you might have heard them talk about a Diff-EQ course or a DE course. That's because if you major in those topics that I just mentioned, you will take a whole course based on these types of equations. So we are just at the tip of the iceberg here, talking about a few of them today. Okay, so some of this is going to overlap with what we've already done, and then some of it will be brand new to tie in with what we've done. Okay, example 1, find all functions y that satisfy dy dx equals secant squared x plus 2x plus 5. So this tells me there's a derivative of a function y, and this is its derivative, and I want to find the functions of y. Notice that it's plural. Okay, so my antiderivative of y, or the function of y would be the antiderivative of this, so that would be tangent x plus x squared plus 5x. Okay, so how many functions can we find? Well, if this is all the information that we have, that this is the derivative, then there could have been some constant, and that's why we put that plus c at the end. There's an infinite number of constants that could be c, so there are technically an infinite number of functions that we could find here. So we call these family of functions the general solution to the differential equation. We cannot find a unique solution without more information. Okay, so when we do have more information, this is called an initial value problem, because they give us an initial condition, and the initial condition is in the form of an ordered pair, and we've done that before. So when we have the ordered pair, then we can pin down that exact function and figure out what c is. So that's what example 2 is. Find the particular solution to this equation. So the derivative of y is this right here, and the graph passes through the point 1, 0. Okay, so this is called initial value because we are giving an initial ordered pair that is on the function, and that's what enables us to find that value of c. Okay, so first thing we do is find that antiderivative. So y equals antiderivative of e to the x is e to the x. Antiderivative of 6x squared would be 6x cubed over 3. So that becomes 2x cubed. And then, of course, there could have been a constant there. So when we have this initial value, we can go further and find c. This means when x is 1, y is 0. So I'll let y be 0, x be 1. And I'm just going to leave e as e. Let's not bother with a decimal. E is more accurate anyway. So 1 cubed is 1 times 2 is 2. And to solve for c, I'm going to add 2 and subtract e. So I'll get 2 minus e is the value of c. So now I can go back and rewrite this whole equation. E to the x minus 2x cubed plus 2 minus e, and that is our solution to the function that has that derivative and also passes through that point. Okay, so if the differential equation is continuous, the value at a single point is enough to determine the unique solution. This is a unique solution once we find c. Why would this not be enough for a discontinuous differential equation? So think of this one particular ordered pair as sort of pinning down the one specific graph or function that we're looking for. as opposed to all these others. Plus c could be positive, negative, so you'd have kind of like this graph that was translated up or down. So this one order pair sort of pins down that one graph that we need to find. But if you have a discontinuous function, say a piecewise function where you have jump discontinuity, or a vertical asymptote where you have infinite discontinuity, then you have different parts of the graph, and knowing this one order pair would really only pin down one part of the graph. So anytime that we have a discontinuous graph that we're finding the original equation for, the initial value only pins down a piece of the curve that passes through that given point. So the domain must be specified with the solution. So, for example, if we had part of a hyperbola where you have two specific curves, it might say, okay, we're solving the part of the equation only for x is greater than 0, so that we would only have that piece of the graph that was in the top right quadrant as opposed to the one that was in the bottom left. So if it is a discontinuous function, we can still do this with it, but we would have specific domain restrictions so that we're only dealing with one piece of that discontinuous function. Okay, example 3. Find the particular solution to this equation, whose graph passes through 0, 3. So this is called initial value problem because this is the initial point that we're given so that we can find C. Okay, so let's find the antiderivative. That would be x squared. Derivative of tangent is secant squared, so that would be minus tangent x. And there could be a constant. Okay, so when x is 0, y is 3. So 3 equals 0 squared minus tangent of 0 plus c. Keep checking that, that this recording is still running. I'm paranoid it's going to stop on me. Okay, so tangent of 0. 0 on our unit circle is over here. Tangent is found by dividing sine by cosine, or if we're dealing with the unit circle, that's the y-coordinate by the x-coordinate. So 0 over 1 gives us a tangent of 0. So 3 equals 0 minus tangent of 0 is 0 plus c. So that means that 3 is our c value. Then we plug it back in that equation. Y equals x squared minus tangent x plus 3. And that would be our specific or particular solution to that derivative problem. Okay, example 4. Find the solution to the differential equation f prime of x, same thing as dy dx, equals e to the negative x squared, for which f of 7 equals 3. Okay, now I'm not even sure what function has this as its derivative. Okay, there are ways that we can find out, but those ways are in a course above AP Calc AB. So we're actually not going to find it. This is kind of one of those magic wand problems. I'm going to say, okay, the antiderivative of this is whatever that is. Not sure what that is, but that antiderivative fits this. Okay? So derivative is that, antiderivative, bam, put that integral sign and the dx on it. That represents the antiderivative. Okay, so f of x is the function that I'm looking for. F of x or y, same thing. But I want to make sure when x is 7, y is 3. Okay, so this right here represents the area under the function, right? Well, I want to make sure that when I get to 7, I have an area of 3. So if this was 0, then I could say y will be 3 if I just add 3 to the 0. Well, I can make this area be 0 if I start at 7 and go to some particular number. Because when I go from 7 to 7, this is 0. 0 plus 3 is 3. So x was 7. I got a y value of 3. So again, another one of those what I call magic wand problems, and we just leave it like that. We have computers, we have calculators that can help us find those things if we don't have the tools yet. Or if you take calculus in college or a higher calculus, then you will find tools to deal with antiderivatives like that. For now, that's our solution. Okay, next thing we're going to talk about, this is new, and that's called slope fields. So in the simplest terms, a slope field is the graphical representation of all possible solutions to a differential equation. In this way, a slope field is very much like a graphical antiderivative. These can be confusing because differential equations don't often look like antiderivative problems. Rather than asking us to solve the integral 2x dx, we are asked to find the function f of x satisfying this. However, this is the core of the antiderivative concept. We're given a derivative and we are asked to determine the form of the original equation. So, given the derivative above, 2x, we can either recognize that 2x is the derivative of anything of this form, x squared plus c, or we could separate the variables and end up with the equivalent antiderivative. Okay, so this right here will be important down the road in a little bit. So let's walk through this and see what else this is really referring to. Okay, so if I said dy dx equals 2x, that means the derivative of y is 2x, and it's with respect to x. Okay, so going from this step to this step. So normally I would say, what happened? But you guys aren't here to answer me, so I'll tell you what happened. This is like when we talked about those differentials, and it's sort of like you're taking dx and multiplying it on both sides, and we get 1 dy equals 2x dx, and the 1 is just that understood coefficient there. Okay, so this is kind of like when we took the implicit differentiation, we sort of tacked on the dx and the dy or d theta or whatever it was that we were taking a derivative of. Similar process there. Okay, so look, from here to here, I integrated both sides. We've never done this before, but we will start soon. You can do anything to an equation, right, as long as you do it to both sides. That includes integrating. So I'm going to take the integral of both sides. The integral of 1 dy, this is when that variable d whatever is important, because if I just have the integral of a number, I need to know what variable it started out as. So the antiderivative of 1 dy is just y. The antiderivative of 2x is x squared, and then we tack on the plus c. Now some of you might be thinking, why didn't I do that? Why don't I say, okay, that is y plus a constant. That is x squared plus a constant. And that's a good question, but if these are just numbers that are added or subtracted, then I could combine them on one side of the equation, either move them all to the left or all to the right, and it would just be a new constant. So normally, what I'm solving for is y. I don't want to junk up that side of the equation with other things. So normally we'll just say, okay, we've collected constants, and they are over here with the x squared. So I just have y equals x squared plus c. All right. Okay, so this is getting into the new stuff of slope fields. Okay, sketch multiple solutions to f of x equals x squared plus c. All right, so for example, I could graph f of x equals x squared plus 0. Okay, that's our normal parabola, vertex at the origin. It's pretty easy to find some specific points. I know that 1, 1 and 2, 4 are on that graph. I also know that negative 1, 1 and negative 2, 4 are on the graph. And that is what that graph would look like. Okay, so that's if c is 0. Well, what if c is 2? Okay, so that means that this graph, basically everything shifts up 2. This will go off the graph there, and off the graph. Okay, so there is that one. And let's do one more. Let's say that I wanted f of x equals x squared minus 4. So c could be a negative number. So now I'm basically taking that first plain old vanilla parabola and shifting everything down 4. Okay, so I could continue to plot different parabolas here with different values of c, but it's basically that plain old x squared plus 0 translated either up or down c units, so that you just have this series of parabolas here that represent all of these functions. Okay, so we're going to graph a slope field for dy dx equals 2x. Now we know what the antiderivative of 2x is. It's x squared plus c. But we're using this simple one here just to show you the connection between a slope field and the original function of that derivative equation. Okay, so what I'm going to do is take this dy dx, which represents the derivative or the slope of a function, slope of a tangent to the original function, equals 2x, and I'm going to generalize for some values. For example, anytime that x is 0, this slope is also 0 because 2 times 0 is 0. Okay, so a slope field, it's a graphical representation like I read to you on the previous page. So when we have a continuous differentiable function, we've talked about how it's locally linear. So if you could zoom in on it enough, it would eventually look like a line because it's a nice smooth curve. Okay, so what we're going to do is sort of take that linear concept, and I'm going to sketch little bitty line segments of a slope of 0 to represent what this tangent line looks like at these points. Okay, now I know that a slope of 0 is a horizontal line. So where x is 0, which is all up and down this y-axis, I'm going to go in and sketch little bitty horizontal segments to represent that slope being 0. So it's just little tiny segments representing the slope at those points. Okay, let's do another generalization. When x is 1, the slope is 2 times 1, or 2. Okay, so a slope of 2, reflect it backwards for you, slope of 2 is a positive slope. Slope of 1 is like a 45-degree angle, so we need to make it a little bit steeper than that. So everywhere that x is 1, which is all along here, I have a slope of 2. So I'm going to try to make it look like a slope of 2. You just do the best you can. And try to plot a slope that represents a rise over run of 2 over 1. Okay, when x is negative 1, all of my slopes are negative 2 because 2 times negative 1 is negative 2. So I'm going to go all up and down the graph, every place that x is negative 1, and sketch a slope or something that resembles a little segment with slope negative 2. Okay, when x is 2. Okay, 2 times 2 is 4, so that gives me a slope of 4. Okay, now 4 is still a positive slope, but it is steeper than a slope of 2, so I'm going to try to visually make it look steeper, all up and down where x is 2. So I'm kind of making a visual representation of what a line with a slope or rise over run of 4 over 1 would be. And let's do one more. When x is negative 2, the slope, or the derivative, will be negative 4. Because I plug in negative 2, I get negative 4. Now x is negative 2 all up and down here. So I'm going to try to draw a slope that would resemble a rise over run of negative 4. Okay, now I'm not going to sub in any more numbers, but as I move out to the right, these are going to get steeper in a positive direction. As I move out to the left, these will get steeper also, but in a negative direction. So, you know, these are, it gets kind of hard to distinguish the difference, but these are very steep over here, and these are very steep over here. Like that. And the idea of a slope field is that you can visually sort of read the graph left to right to figure out the slope of the original curve. Again, we know this is a parabola, but if we didn't, then I could view this and sort of see the flow of it. So I could see like, okay, this is coming down, and I may be missing the mark a little bit, but it goes back up and becomes steep. And then I've got this over here. And you just sort of follow the flow of the graph. And so I could see that this is representing a bunch of parabolas. So these are useful when you don't have a function equation or it's hard to find it or visualize it. You can look at a slope field and get a feel for what the original graph would have looked like, just by examining those little segments representing slopes. Okay, so the next example, we are going to graph the family of functions that solve the differential equation dy dx equals cosine x. Okay, so any function of the form y equals sine x plus c solves this differential equation. So we know this already. I don't have to have a slope field to figure this out, but what I am going to do is just graph a series of sine x plus c functions, kind of like we did x squared plus c. So let's sketch sine x plus c for all of these c values. Now when it's 0, then that's just sine x plus 0. So that's our normal sine curve. Okay, look at the scaling. This is our domain. This is our range. Okay, so on the x-axis, this is going from negative 2 pi to positive 2 pi. Okay, that means that that is pi, and that is negative pi, and that's pi over 2, and then 3 pi over 2, etc. And then the y-axis is going from negative 4 to positive 4. So each of these represents just one. Okay, so sine function crosses the origin, hits a max of 1 at pi over 2, comes back down at pi, hits a min at 3 pi over 2, and goes back to 0 at 2 pi. Now, you should hopefully remember the gist of this. For example, the period of a sine curve is 2 pi. So I should finish my full up-down curve from 0 to 2 pi. It goes up first and then down. So halfway through this, I should be crossing back over the x-axis on my way to complete that down loop, and then back at the x-axis at 2 pi. So if you can just remember that general pattern, we can just sort of make this fit in. And of course the opposite thing is happening over here. So I dip down, back to the x-axis, go up, and back down. So that would be for c equals 0, just your plain old sine curve. Okay, let's do for c equals 1. So basically all of these things that I just graphed shift up 1 unit. So all those points that I just plotted, sort of following them along and moving everything up 1. It's kind of pretty. All right, let's see this color. Let's make c equal 2, so sine plus 2. Well, now all of these are moving up 1, which means a total shift of 2 from the original graph. Okay, so that's so pretty. So that's for c equals 0, 1, and 2. So let's do c equals negative 1. I'm going to shift down 1. So that's for c equals negative 1. Now, we'll do for c equals negative 2, so sine x minus 2. And so these are just going to shift down again. Okay, So that represents a family of functions that fit this derivative, because we don't know what c is. Now c doesn't have to be one of these values here, but it could be. It's just representing what the whole family of solutions would look like. Okay. Oh, look at this. And it looks so much cooler in color. I hope it's still recording. I lost my video for some reason. Hang on, I'm about to break something. Okay, I think we're okay now. Oh, I guess I keep touching things. Okay. So in 2014, I was very excited, and that seems like so long ago now. But I saw this article pop up online on CNN, and they had this whole article. You can see that this was actually a video that would play, but it's a slope field. And what it is a slope field of is a bunch of astrophysicists got together and studied Big Bang, gravitational waves, etc. And they put together this video of what they thought the gravitational pull and waves due to that during the time of the Big Bang were like. And the whole graphical presentation is slope fields. So, I mean, this is a chaotic slope field, but a slope field nonetheless. So you could, I mean, it's just like we talked about. It's a graph with a bunch of little tiny segments representing slopes at different points. And I don't know that you could say there's a flow to this or not. Again, it's kind of chaotic, but I was just so excited when I found it, because it's like, oh my gosh, this is a real slope field, and this is current astrophysicists using these slope fields to try to make sense of something that happened so long ago. So there you go. I don't know if you can still find that article or not, but I put the link there if you wanted to try. Okay. If we want to produce a graph without actually solving a given differential equation, we can sketch a slope field. Since a differential equation gives the slope at any point xy, we can use that information to draw a small piece of the linearization at that point, which, because of local linearity, approximates the solution curve that passes through the point. Okay, so these are our steps that we're going to find, or go through to find this slope field. When sketching a slope field, consider the following important aspects of the equation. Where's the slope 0? Where is the slope undefined, if at all? Where is the slope 1 or negative 1? And where is the slope positive or negative in general? So we kind of did that with this slope field that we plotted back here. So I was just saying, okay, anytime that x is 0, the slope is 0. Anytime x is 1, the slope is 2. So we're just generalizing patterns in order to sketch these slope fields. Okay, so here's one. Construct a slope field for dy dx equals x over y. And this will be needed when we get to example 8. This is part of example 8. Okay, so all I know is that the derivative is x over y. Okay, so if I look at those generalized questions that were listed back here. Okay, so where is the slope 0? All right, so where would this slope be 0? It would be 0 anywhere that x was 0. So slope equals 0 when x is 0. All right, well, where is x 0? All along here. So I'm going to make, I think this pink shows up a little bit better. I'm going to make little horizontal segments representing a slope of 0 every place that x is 0. Okay. Where's the slope undefined? If it is, oh, this one is. Since I have a denominator that has a variable in it, anytime that y is 0, the slope is undefined? Okay, so a slope that's undefined means you have a vertical line. Y equals 0 all along the x-axis. That's where the line y equals 0 would be, right? Resting on the x-axis. So every point on here where y is 0, I'm going to kind of simulate a vertical segment which would have a slope that's undefined. So undefined slope, all along here. Okay, now clearly at the origin I can't have a slope of 0 and undefined, so my guess is that graph may not even exist there. We'll just have to see what it looks like. Okay, so let's keep generalizing. Where is the slope 1 or negative 1? Okay, so this slope would be 1 anywhere that x and y are the same exact number. So that includes negatives, right? So slope is 1 where y equals x. Okay, well, y equals x is this line that goes straight through both of these quadrants and through the origin. Slope of 1, y-intercept of 0. Okay, so any point along that line, I'm going to try to sketch a slope of 1, so a rise over run of 1. So that's a 45-degree angle, right? Okay, well, again, we know all this stuff can't happen here. That's okay. Hopefully our shape will come to light as we sketch some more. Okay, so I included the negatives. -1, -2, -2, etc. would all have a slope of 1. Okay, what about, where's the slope -1? Well, the slope is -1 wherever y and x are negatives of each other, right? So where y equals -x, well, that's the line here. So all along that line, I would have slopes of -1. So I'm going to try to sketch these so that they look like slopes of -1. Okay, that's not real helpful yet, is it? Okay, what about, just in general, where's the slope positive and negative? Well, if both of these were positive or both were negative, then I would have positive slopes. So in these two quadrants, I should see positive slopes. This whole fraction will be negative if x or y, or if they have opposite signs. One is positive, one is negative. So that would be in these two quadrants. So what I would do from here is probably just pick some points. For example, what if I use the point 1, 2? Okay, so for 1, 2, I would have a slope of x over y. So I would have a slope of 1/2. So not as steep as this, right? It's going to be less steep. Okay, what about the point 1, 3? Well, x over y, that would give me a slope of 1/3, so that's even less steep. Okay, well, what about this point here? That would be 2, 3. So that would be the slope 2/3. Okay, well, that's a little steeper, isn't it? I mean, not a whole lot, but a little bit. Let's see, what about a point like 2, 1? I'm sorry, yeah, 2, 1. So that would be 2 over 1. Oh, that got steeper. Okay, so this is going to go up like this. Okay, what about 3, 1? And you could probably do these in your head by now. You're seeing what's going on. Well, that's a slope of 3 over 1, so that's even steeper. Okay, and this would be a slope of 4. And this would be a slope of 3 over 2, so a little less steep, a little less steep. So you're just sort of looking for patterns there. Okay, what about, we don't have to do every single one of these, but you tend to want to get sort of a picture of what's going on. Let's do 2, -1. Okay, x over y would be 2 over -1, so that's a slope of -2. Well, that's a little bit steep. Okay, this would be a slope of -3. That's even more steep. And then this would be steeper yet. Okay, I could kind of see a curve developing there. See what I mean? And then it sort of looks like a curve developing here. Okay, so let's do like maybe just a couple more down here and see what's going on here. But I would definitely say that I see this curving here. Maybe like a hyperbola. You know how hyperbolas can look like that or like that, in addition to the ones that we deal with a lot. So you have two curves in a hyperbola. They can be opposing curves up and down or horizontally. Or they can be two curves like this. So it's kind of looking like maybe one of these or maybe even one of these to me. Okay, let's just try a couple more. So what about 1, -2? Okay, so that would be 1 over -2, so a slope of -1/2. So kind of flat. Okay, this would be 2, -3. How about that one? -2/3. Okay, so -2/3 would be a little steeper than that. And now I can't even remember where I was. Okay. Oops, down here, my bad. Okay. Alright, so yeah, that even looks like it's curving up a little bit just for those couple of points there. Okay, so we could keep going, but I think that's plenty to sort of get the feel of. When you get to example 8, or when we get to example 8, it's a matching problem. So just looking at what I see here and what we already found, I would say that when we have to find this slope field, I'd say it's going to be that one because we were already sort of seeing that come through. Okay? And so that explains why all the points we're going through here, that point's not even on the graph. So I definitely have some curves coming like this, and I would imagine this one is over here. So when I look over here, I would already say that A and 3 match up. I'll just put an A above that. Okay. All right. This one down here, the slope field is already made for us. But what we're going to do is use the slope field and this differential equation to sketch a graph of the particular solution that passes through the point 2, 0. Okay, you can definitely see on this graph that there's probably an asymptote right here, a diagonal asymptote. And it looks like the curve is kind of doing this above it. And I'm not sure that this is really anything on the graph, but there could be another piece down there. But all we're going to do is take the point 2, 0, find it, plot it, and then follow the curve and make our curve go through this point. Okay, so let's see where the point 2, 0 is. Looking at your scale, remember this is domain, this is range, and I want to find 2, 0. So if this is going out to 4.7, that's a strange number, and -4.7. So let's see, this looks like maybe, see how there's kind of a column here? I'd say that's probably 1, 2, 3, 4, oh, I don't know. All right, I'm going to guesstimate 2 zeros about there. Okay, that's about as accurate as I can do based on what I'm given. Okay, so if I follow the flow of the graph and make it go through this point, wouldn't you kind of say that it's kind of coming up this way and then kind of coming around this way? I'd say it's something like that. I don't know what that equation would be. I don't know what you would call that graph. But just following the flow of the graph, it looks like maybe that's what's going on. And that's all we're doing with this one. So just sort of trying to visualize what the original graph would look like based on the flow of the graph. Okay, then our last example here. Match each slope field with the appropriate differential equation. Okay, so we're not going to have to graph a whole lot of detail for these because we're going to look for those generalized things. Okay, so I think we already figured out number 3. Let's go to number 4. And this has kind of opposite here of what was going on here. So for number 4, I would say it has a slope of 0 when y is 0. And that's because y is in the numerator, a fraction is 0 when the numerator is 0. Okay, so where's the line y equals 0? All along here. So I'm going to look for a graph that has slope of 0, so horizontal segments around here. And those are approaching horizontal, so they could be horizontal on the axis. Those are also maybe, this is not. I would definitely say this one does not apply. I would say it's narrowed down to C or D. Okay, so let's keep going. This one, number 4, the slope is undefined when x is 0, because x is in the denominator. Fraction's undefined when the denominator is 0. Now, an undefined slope looks like a vertical segment. So where is x equals 0? All along here. These are not vertical segments. These could be vertical. Okay, we already eliminated that one. So I would definitely say that 4 has to go with C, just based on process of elimination there. Okay, so I'm not having to plot a whole lot of points. I'm just generally looking for patterns that I know would have to be true. Okay, let's go to this one. Number 2, let's make some notes. Okay, when would this be 0? Well, that would be 0 if x or y was 0. So the slope would be 0 when x was 0 and when y is 0. Okay, so x equals 0 along the y-axis, y equals 0 along the x-axis. A slope of 0 is horizontal. So I'm looking for a graph, and we only have B and D left, that has a slope of 0 on the x and the y-axis. And the only one that really fits that description is this. I have little slopes of 0, and these are approaching little slopes of 0 here. So it could be 0 on there, and they're just blending in with the axis. So I would definitely say that this one matches D. Okay, and let's just look for something that does verify that B must go with number 1. Okay, so when would this be 0? This would be 0 when x and y were the same number. When y and x are the same number. So again, that was that horizontal line, y equals x, and a slope of 0 would be horizontal. So, which one are we missing? B. So if I go along this horizontal line, do I see little slopes of 0? I don't know that I do. Okay, let's try something else. We might just have to go with it because it is process of elimination, maybe? I'm definitely not. Of course, so I don't know the scale of that. Because look, I do see kind of little going towards horizontal there, and kind of like there's one. So the scale might be distorting it just a tad bit, maybe. I don't know. I would definitely say process of elimination, that has to be B. I don't know. That one's kind of weird. I'm not really liking that, but I do feel confident about those other 3. So I think we're going to have to go with B on that one. Okay. All right, now I believe that is it. And hopefully my recorder, my video, kept videoing the entire time, because I don't think I'm up for doing this 3 times in a row, since I haven't gone home after the parade, and the football game has already started. So I'm ready to check out. Okay, I hope you guys have a great day. I am going to work out all the homework problems, and I will post those, and I hope to goodness that I'm back after a day or two. So keep your fingers crossed for me. Bye, guys.